So, as far as I know, the last lectures that you had were on basically probability distributions in general and some notions of probability. And these are really important because these are the elementary building blocks that you use later on to formulate perhaps very complicated models that you use in computer vision. This could be classification, this could be image infilling, there are loads of applications, and they all use these elementary building blocks that you got to see perhaps last week. And basically what we're going to talk about today is how we can, once we've decided on a model that is appropriate for our task, this is often the most difficult challenge that we face when we want to solve any problem in computer vision. So once we've decided on a model for a probability distribution, how we can learn the parameters of that probability distribution from data. Okay, does that make sense? Yeah. So an example would be we want to model the color of, say, the pixels of apples in images, right? So if we want to model that, we first need to pick an appropriate distribution to describe this data. Any suggestions what this might be? Use a Bernoulli distribution, or perhaps a Gaussian would be like the first approximation if we assume that they are continuous valued, the colors, or say the red channel is continuous valued. And then we would need to estimate the parameters of that Gaussian from data, from training data. Basically, how we estimate these parameters, how we fit a probability model, or how we do learning, this is what this talk is about. So all these terms, fitting, learning, or sometimes inference, they're often used synonymously. Okay? And basically what I'm going to do is I'm going to describe three methods that can be used for this purpose: maximum likelihood, maximum posteriori estimation, and the Bayesian approach. And I'm first going to describe them in a fairly abstract way, and then I will start to work through two examples. Probably will get stuck in the middle of the first example, and this is going to be continued in the next lecture. Okay. I hope this intuition makes sense to everybody, or the question that we're trying to address. So let's jump right in. So maximum likelihood is perhaps the most basic way of fitting probabilistic models. And the idea here is that we choose our model, right? This is some model that we define. This has some parametric form. It could be a Gaussian distribution, for instance. So we choose our model, a parametric form like a Gaussian distribution, and we collect some data. Okay? So we would, for instance, in the example that I brought up earlier, where we want to estimate the distribution over the, say, red channel of apple pixels in images, okay? We would collect a bunch of images that contain apples, select those pixels that actually belong to an apple, and this would be our training data, right? These would be our data points, x1 to I. So this is capital I, and we have I different data points. Now, how should we potentially choose, what would be one way, an intuitive way to select the parameters for our distribution that's supposed to describe that data? No idea? So it's here on the slide, actually. So the core idea is that if this distribution with parameters theta is supposed to have generated that data, right? This is sort of the assumption that we're making when we're modeling. Then we probably would want to choose our parameters such that this data is likely under the model. Okay? Does this notion make sense to everybody? If not, please cry out now, because this is sort of crucial to what's going to come in the rest of it. Yeah? So we want to choose our parameters such that the data is likely under the model. And more specifically, we want to choose the parameters such that the probability of the data that we have collected. So this data set is fixed. This is important to remember in the rest of the talk. We have a fixed set of data, x1 to xi, is maximized. Okay? So we treat our probability distribution, or density, now no longer as a function of the data, but as a function of the parameter where the data is fixed. Okay? And then we choose the parameter such that this function is maximized, or this arg maximum. Choose the parameter such that the probability of the data under the model is maximized. Okay? Now, typically, we make an assumption, which is that these data points that we have collected are independent. Okay? So each of those pixels, we assume, are independent draws from this Gaussian distribution, right? For instance. And if we make this assumption, then we can rewrite this joint distribution over the data as a product over the individual data points. Does this make sense? Okay. Now, typically what we have, once we have estimated the parameters of our model, we want to use it to do something, right? So for instance, if we are given a new image and a new pixel from that image, and somebody tells us, oh, this pixel was part of an apple in that image, then what we might want to do is we might want to evaluate how likely is that pixel. Yeah, sorry?
Sorry, I didn't want to interrupt.
Oh,
yeah, I have a question regarding the product. So the pixels are not independent.
Right, this is an interesting question. So let's assume, so when would they be independent, when would they not be independent? It's a very important question. So if I gave you one image with one apple, and I told you, oh, use all those pixels from that single apple in that image to estimate the distribution, or I gave you, say, 100 images, each contains an apple, and I told you use one pixel from each apple each to estimate the distribution. In which case do you think this assumption makes more sense than in the other?
In the latter.
In the latter, yeah, because across images, those pixels are likely to be independent and reflect the true distribution of colors of apples, right? Whereas if we just pick all those pixels from one single apple, if that apple happens to be red, then we'll be missing out on all the apples that are green, for instance.
And another question, maybe you keep talking about the pixels. We have somehow labeled the pixels, but in reality you would have just labeled the pictures.
Okay, so we assume that we have training data that is appropriate for our modeling task. Yes, but in reality you would need to have somebody who labels that image first, of course. Yeah, so but we assume we have the right data to estimate our model. We don't always have that, and this is another problem, but we're not going to talk about this. Okay? Right. So once we've got those parameters, we can, given a new data point, evaluate, for instance, the probability or the density of that data point under our model. And this x star will be denoting the new data point. Okay? Right. So this is maximum likelihood. This is sort of this kind of simplest case. Now we're going to talk about something that is very similar, which is maximum a posteriori estimation. Now, in the previous slide, we didn't make any assumptions about what values of the parameters are plausible and which are not. In many cases, however, we might have some prior knowledge about plausible parameter values. Okay? And this prior knowledge we can capture in a prior distribution over the parameter values. Right? Say if we were estimating pixel the color of Gala apples, which tend to be red, we might believe that our parameter should have a high value in the red channel, say. Okay? We can capture this prior knowledge in this prior distribution over the parameters. And what we do in maximum posteriori estimation is we pick our parameter estimate such as to maximize the posterior probability of the parameter given the data. So we have a prior distribution over the parameters, capturing our prior knowledge. We are given our data, which is modeled by the data likelihood here, which we had on the previous slide, right? And then we maximize the posterior distribution. This is the posterior distribution here, and we can compute this using Bayes' rule from this likelihood term and the prior distribution. And we have to normalize it. Okay? Now, if we make the same assumption as before that our data points are independent given the parameters, right? We can rewrite this as a product, which simplifies things a lot in the process. And typically we can simplify this further because this denominator here, which normalizes our posterior distribution, doesn't depend on theta, right? So if we want to maximize this expression with respect to theta, we can just ignore this. So we can maximize just the numerator here. Okay? And once we've picked our parameters such as to maximize that expression, we can then again use it to evaluate the probability of a new data point under that distribution. Okay? Now, maximal posteriori estimation takes some prior knowledge about the parameter values into account. And we choose our parameter estimate, the parameter estimate that we use for any further applications, right? Such as to maximize the posterior distribution over the parameters given our data and this prior knowledge. Okay? Now, is that a sensible thing to do? Think about the perhaps shape of the posterior distribution, in which case this seems a sensible thing to do, in which case it might not be such a sensible thing. Any suggestions? Perhaps. So let's assume this is our parameter. These are the possible parameter values, theta. Okay, and this is our one posterior distribution that we compute. This should look nicer, obviously. And the value that we would pick with maxima posteriori would be theta hat, right? So this is P of theta given our data. Now, perhaps this distribution has a different form. Perhaps it looks really like this. Okay? This could be another distribution that we get. Now, does picking the maximum of that distribution still make sense? Well, perhaps if we have to confine ourselves to a single parameter estimate, it is the best thing we can do. But really, there are many possible parameter values which are all almost equally good, right? Which all have almost equal high probability under the posterior distribution. So we don't want to confine ourselves to a single, so I hope people can actually see that, to a single parameter estimate. But really, we want to take this uncertainty as to what are good parameters into account. Okay? So this is what it says here. There are many possible values that can explain the data. And in the Bayesian approach, we try to kind of take them all into account. And we do this by first computing our posterior distribution over the parameters given the data that we've observed so far. Yeah, this is the same thing that we had in the maximum posteriori estimation. And then to evaluate the probability or the density of a new data point given this posterior distribution, we average basically, or we take a weighted sum over all possible values of the parameter, and then evaluate this data point under the likelihood for all these possible values. Okay? So you can think of this as a sum over all possible parameter values, or an integral of it. So this captures much better the uncertainty that we have, the uncertainty in the parameter estimate. And you'll see the effects of this in the work examples. Okay. So this is an overview, basically, over how we use the parameter estimates that we got from our different estimation methods to make a prediction It's just a summary, basically. Both maximum likelihood and maximum posteriori estimation give us a single best parameter estimate according to some criterion, and we use this and we then evaluate a new data point under the model given that parameter estimate. Okay. In the Bayesian approach, instead, what we do is we compute the full posterior, and we then consider all possible values under this posterior. Some will be more likely than others, and basically average the likelihood term here by taking a weighted sum with respect to the posterior probability of the term. Okay. Now, there's actually a view that unifies these three different ways of making a prediction, which also emphasizes sort of how we lose information if we take one of those two routes. We can look at basically the way we make a prediction for the maximum likelihood and the maximum a posteriori approach, also basically as an integral here. And in the maximum likelihood and the maximum posteriori case, basically our posterior distribution, not the real posterior, but our distribution over the parameters that we estimate is simply a delta p. So it's a distribution that is p at a single value, right? So there would be a distribution that only has basically which is non-zero here at our estimate, right? And then we can look at the way we make a prediction as an integral of the likelihood of the new data point given the parameters and with respect to that distribution, this delta distribution. Okay, and then we get exactly this prediction that we have seen before. Okay, this delta peak is a sort of this funny construction. In the discrete case, perhaps it's just an indicator function that is 1 for the right value. In the continuous case, it's a bit more complicated. But basically, it's non-zero only if theta is equal to theta hat. Okay. So this is sort of the high-level abstract overview over the different ways of estimating parameters in an abstract manner. Now we're going to start and work through 2 examples. Are there any questions so far? No?
Just for understanding.
Yes.
So if we are at the Bayesian approach and we do this integral, we have this nice graph there with the 2 maxima on the whiteboard. So can you say where the Bayesian approach, will it somehow then be a weighted like center of mass or something, or you cannot say it will pick one value?
No, it doesn't necessarily correspond. In some cases, you can compute a single parameter value which corresponds to this integral, but not. It really depends on the nature of the distributions that you're considering. Yeah.
So, are we the maximum likelihood and the maximum posteriori that one?
Yeah.
We lose data if we use those, but the Bayesian we don't.
I guess you can think about it like that. Yeah, you lose information about the data.
But we don't if we use the Bayesian.
Yes. To the extent that your model captures the properties of the data in the first place.
So if you have what do you do with your different? If you use the Bayesian approach, you're getting multiple sets of parameters. You get like a range of parameters that will fit your model. So what do you do with? So how do you then make a decision to build a?
Well, this is what's shown here, right? So you can make your prediction by computing. Sorry, so this is not the right integral. This is the right integral. You basically average your predictions over the different parameters, and you weight each parameter by its posterior probability.
So basically, the probability of x given beta is probably giving some sample contains some errors.
Sorry, say it.
The probability of each x given beta will contain, well, when we start with a sample, it will contain errors. So the sample will not represent the reality completely, so it will not be perfect. So there is an error in it. Now we multiply it with another probability that we derived, which also has errors. So how do the errors then impact the optimality of this approach in respect to the two other ones?
Well,
More error prone if you have a biased sample, and every sample is biased.
okay. So I wouldn't say that I guess it depends on what you mean by bias. If it comes from the distribution that you're assuming, it is perhaps noisy. It's not really noisy, not really biased, perhaps. But you're right. And we basically lose. Here we are committing to, in both of these approaches, we are committing to a single parameter value, ignoring our uncertainty about what is actually the right parameter value. Okay? So the parameter value that we pick here is optimal for our sample, but it doesn't necessarily reflect the true distribution. The true distribution over parameters, to the extent that we can reason about it in the first place, given basically our model, is captured by the full posterior distribution. So here we commit ourselves to something that is possibly not optimal, right? This is exactly what happens if, say, we pick that point here, which seems best given the data that we've seen so far. But really, there are all these values which are all pretty good, and which we should consider as well. And perhaps with a slightly different sample, this would be looking slightly different. So really, those approaches sort of, here we prematurely commit ourselves to single parameter values, whereas here we don't. This is why you get sort of overfitting if you do maximum likelihood estimation, or also in the maximum posteriori case, especially if you have a small sample. If we have a lot of data, ultimately this posterior distribution will become very peaked and will look very similar to the likelihood term.
Okay, but everything will look all three of those methods will be very peaked if you have a lot of data. So.
True. So all I was going to say is that this posterior distribution will converge basically to the maximum likelihood estimate if you get a lot of data. Because then the data dominates, ultimately, if you have a lot of it. If you have little data, then you have all this uncertainty, which I was sort of drawing here, and you will take this into account. You might get a more uncertain prediction here, but that is right, because you just are not certain about your parameter values.
Right.
Okay? We can talk about this afterwards if you're not satisfied. Okay, so the first example that we are going to consider is the normal distribution. And this is just a reminder. So we're doing parameter estimation, so we need the parametric forms of the distribution we are working with, right? So this is the parametric form of the density of the Gaussian or normal distribution. It has two parameters, the variance sigma squared and the mean. Right? And there are a couple of examples drawn here. Can you read those numbers at the back? So the red one is a distribution where the mean is 0 and the variance is 1. The blue one has a mean that is larger than 0, 1.5, and the variance that is larger than the one of the red one. It's 4.4, I think. This is why it's more spread out. Right? And the green one has a negative mean and the variance is smaller than the one. I guess you remember that from your previous and we're also going to write it like this. this sort of emphasizes that you're looking at it as a function of the parameters, and sort of the data is less important. That's what we fix. Okay. Now the other thing we need, this is enough for maximum likelihood estimation of a Gaussian. To do maximum posteriori estimation, or also to do fully Bayesian parameter estimation, what we need is a prior distribution over the parameters, over our mu and our sigma. Now, in principle, we could pick any distribution that we like here, or that reflects almost any distribution. There's some constraints, but any distribution that reflects our beliefs about these parameter values, or prior beliefs of these parameter values. The normal inverse gamma distribution is particularly nice. Has anybody got any idea why? I think it's something you should have been reading about. I was told correctly. Yeah.
Make sure that the variance doesn't get negative, or doesn't get.
Yes, these were the constraints that I was talking about, but there would be many distributions with which we could ensure that. Any other?
It's a conjugate prior for the.
Yeah, can you sort of briefly say what that means?
The posterior will be also a Gaussian. The posterior probability will be also a Gaussian if you take this prior.
Yeah, it's not going to be, so this is a joint distribution over mu and sigma, and if you compute the posterior, given some data, we'll get basically a posterior distribution over mu and sigma, given the data, that is also a normal inverse gamma distribution. But you're right in the sense that actually you can look at this distribution as two, in a way that it has two components. So it's basically a gamma distribution, or an inverse gamma distribution over the variance, and then we pick our mu conditioned on that variance that we have chosen before. Okay? So you can just in case you're interested in this, you can write this joint distribution over mu and sigma squared, which has 4 parameters. You can write this as, you can decompose this into 2 components. One is the conditional distribution of mu given sigma squared. Sorry, this should be delta times the probability of sigma squared with parameters. Okay, so we first pick a variance and then we pick a mu that depends on the variance. And basically, the effects of this distribution, this is shown here. So, as you were saying correctly, the sigma squared is always positive in this distribution. And the alpha and beta parameters mainly control, basically, they control the distribution over the variance. Okay? And this is what's shown in the first 2 plots, varying alpha and beta. They're called also, I think, the shape and rate or scale parameters, respectively. And then the other 2 parameters, the gamma and delta, they control basically this conditional distribution over mu here. And in particular, the gamma, the delta controls where the mean is of the mu. Okay, we can see that here. If we change the delta, we shift the mean of the mu. And the gamma controls how the variance of mu scales with the variance that we have with the sigma squared. In general, what the important thing to notice is that basically, as we increase sigma squared, right, the possible mu values will be spread out more widely. And intuitively, that makes sense if you think about inference. So, if we believe that we have a large variance when we try to estimate parameters, right, we'll be less certain about the possible values of mu than we are when we have a very small variance. Everybody happy with this? I mean, these plots are important. They make sense to everybody. So it's a heat map of the density of the joint distribution over mu and sigma squared. So bright yellow values mean high probability of this combination of mu and sigma squared values. Black values, so very dark red values mean very good. Okay, so these are our two ingredients for the parameter estimation. We have the likelihood term, this is the Gaussian density, and we have the prior over the parameters, which is our normal inverse gamma distribution. This is the conjugate prior. Okay. Right, so we're going to start with maximum likelihood estimation. Now, this is what we've seen before. So we're given some data, x1 to xi, and given that data, we want to estimate the parameters of our Gaussian density of this distribution such as to maximize the likelihood or the probability of the data under that distribution. Okay? Theta here are mu and sigma squared. Right? Now, we assume that our data is independent. We discussed that before, so we can rewrite this as a product here. And then what we plug in is the density terms, the Gaussian densities here for each individual data point. Okay? And this is just reproduced here. Okay, let's go through this step by step. So we get a product over the individual data points. So we get one of these terms that we've seen in the previous slide for each data point. And we multiply them together. And if we do that, we get an expression that looks like this. Does this make sense to everybody? How we get basically from this expression here for each data point to that expression here, which is sort of the product of these normal densities for all data points? So basically, is this too basic? Or does everybody see that? Perhaps I write it down. Okay? Okay, good. So basically what we have at the front is just I times the normalization constant of an individual Gaussian. And this here is the product of the x terms for all the Gaussians. And the product of x terms turns into a sum in the exponents. Right? So these are the individual terms for the individual data points. We just sum them up in the exponents. This is sort of basic. Now, our data looks like what's shown here on the x-axis. These are always the same data points. And what is drawn here is basically the density for 3 different possible values of mu and sigma. Okay? Now, to compute this likelihood of the full data set, we multiply together the values of the density at the data points, right? Now, I'd like some guesses as to which of those 3 possible values for mu and sigma is probably the best one, especially for those who can't read the likelihood values that are written in the figures. Have some people from the back, because you're less likely to be able to read the numbers. The third one? Can you reason why?
It seems to be centered around the mean and the least spread out.
Yeah. So what's the problem with this one over here?
Which one?
This the one on the very left?
Well, the mean is just doesn't suit the data properly.
So basically, we are wasting a lot of sort of probability mass over here where we don't actually see any data. Right? And because this has to integrate to 1, this lowers the density values everywhere else. So here we are wasting probability mass in this area. What's going on here? Just really nice and tight, isn't it?
Use the data point.
Yeah, so basically here we have this one data point which has a really low value of the density or probability. And because we're multiplying them all together, this gives us a very strong penalty. Right? So this is really the one that is the best compromise in terms of width and it's also nicely centered around the method. Okay, this is just a different plot. So this is, again, we fix our data set, and then we plot the likelihood as a function of mu and sigma. Okay, and this is what's shown here. This is not a joint distribution. I mean, you can't see the scale anyway, but this here doesn't have to integrate to 1 because it's just the likelihood. So if you look at it as a function of mu and sigma, it doesn't have to integrate to 1 in this case. And basically, the best parameter value, or the one that has, where this likelihood has the highest value, is again the one that's shown here. It's our maximum likelihood estimate. This is what's indicated by the cross. And these are the parameters. This is the Gaussian that corresponds to the parameter values at this point. Okay? Everybody happy with this? Right. Now, how do we get our estimate algebraically instead of just plotting this function and looking at it, which we can do perhaps if we have a one-dimensional Gaussian, but in high-dimensional spaces, that's quite difficult. So formally what we want to do, we want to maximize the likelihood with respect to mu and sigma. We've seen that before, so this is just the product of individual data points. Now, we could try to do this directly, but we can simplify our problem a bit by considering the logarithm of this term here. Right? So if we take the logarithm of this, or equivalently of this, and maximize the log of that with respect to mu and sigma, we basically end up with this expression here. So does this make sense to everybody? So the product of the logs, so we take the log of this whole expression, so this product turns into a sum, right? And then we can decompose the terms that we see here that way. So we have I times the normalization constant, the first part of the normalization constant. This is the part that depends on sigma. Again, I times because we've got I data points. And then we have the terms in the exponents as a sum. Does this make sense? Yeah? Now, why can we do that? Or why do we want to do that? Well, we can do it because the logarithm is a monotonic function. So if we have a function that we want to maximize, right, and then we take a monotonic transform of that function and maximize it, maximize this transformed function, clearly the peak is going to stay at the same point, right? So if, yeah, that should be clear. Now, the nice thing about this transform is that basically this nasty product up here decomposes into sums, and the x's, which we actually have in many distributions, disappear, right? So this looks perhaps a lot, at least to me, it looks a lot nicer than this if we want to maximize it, okay? So the product turns into sums, and we almost always have a product because we assume typically independent data points, and in many distributions we have x terms which also disappear, basically, or the x disappear. And this is why we take the log. And this is then also called the log likelihood. So this, whereas this is the likelihood of the data, this here is called the log likelihood of the data. Right? Now, how do we maximize this log likelihood? It's often denoted by L, this log likelihood here. Right. Well, the usual speed, we take the derivative with respect to the parameters and set the derivative to 0. So what happens if we take the derivative of this, which is the big L, with respect to mu? Well, those two terms drop out. We are only left with this term, and this is basically the derivative of this term here with respect to mu. Okay? Now we set it to 0, and then we can solve for mu. Okay. And I guess, intuitively, does this make sense? What is this? Yeah, it's just the average. So that seems like a sensible thing, right? Okay, we can do the same for the sigma. There's a minor increase in difficulty. And basically our estimate of sigma is simply the sum of the square deviations from our estimate of mean, again, average. Okay? Again, this kind of makes sense. And you've probably seen this before. Now, one thing you've probably heard about quite a lot, especially in sort of a regression setting, is doing a least squares fit, right? Now, we can interpret this idea of least squares fit in terms of fitting a Gaussian, or the mean of a Gaussian. So, if we try to maximize this log likelihood with respect to mu, the only thing we need to worry about is this term, because those terms do not depend on mu. So we end up with this expression to maximize. Now if we pull the minus here outside, then we end up with this term to minimize. And this is just pick mu such that the square deviation of all our data points from our mu estimate is minimized. This is what sort of least squares fitting is about. And in a regression setup, this mu is perhaps a function of some parameters. So the thing is a bit more complicated, but the idea is the same. So if people say we do least squares estimate, they typically assume a Gaussian noise model, right? Basically estimating the mean with a Gaussian distribution. Okay, yeah?
What's sigma in this case?
Well, sigma is fixed here. So we don't, well, you could estimate it as well. Or you can pick your favorite value. I mean, if you have perhaps no sigma, often it's just assumed to be 1. It doesn't affect the mu. So no matter how you choose sigma, it doesn't affect the mu here. It will obviously affect the prediction. Yeah.
So where did the motivation for these squares come from? I didn't get the jump from the maximum likelihood, where we had mu and sigma, to this slide.
It's equivalent. So if you only fit mu, the two things are equivalent. It's basically least squares you can think of as fitting the mean of a Gaussian distribution. And typically, in the regression setup, you have some input data and some output data, and from the input data, you want to predict the output data, right? So typically, this mu will be a function of the input data. So you want to predict the output, which would be x, and you have some input, so you estimate a function of the input that predicts x well. And this is sort of the least squares fit. Okay? But the two things are basically equivalent. Right. So this is maximum likelihood. Now let's quickly go through the map setup. Here what we want to maximize is the posterior distribution. And again, this term is a product of the individual data points, where we plug in our likelihood for each data point, and then we have our prior here. Now, this is just a reminder of what the prior looks like. It's our normal inverse gamma distribution, and basically what this plot shows here is the joint distribution over mu and sigma, and this is the mode of this distribution, basically where it's peaked. It's shown as the purple cross, and then these blue crosses here show samples from that distribution. So pairs of mu and sigma, right? Or sigma squared, really. And the Gaussian distributions that correspond to the mode, so to the peak of the joint distribution, and to those individual samples are plotted here in blue and purple, respectively. Okay? So these are all Gaussian distributions with parameters that correspond to one of those crosses. Okay? Which one is this most likely to be? Which of those crosses? Shout when I point to it.
That one.
That one?
Yeah, the left one.
This one?
Yeah.
What would be the mean here? Would be negative, right? So this one does indeed correspond to that one, I believe. Why not this one?
It's got smaller variance.
Yeah, because the variance is smaller here. Okay, so it's a tighter thing. The variance is smaller. Okay, so fitting a normal, basically doing maximal posteriori fitting with Gaussian likelihood and normal inverse gamma prior. We maximize this expression here with respect to mu and sigma. This is just the right fit, plugging in the appropriate densities. Okay, and the effect basically of the likelihood and the prior term and the corresponding posterior are shown here in those three panels. So this is just a plot of the likelihood. So the plot of this term is a function of mu and sigma that we've seen before. Okay, this is the likelihood that we've seen before. This is the prior term that we've seen on the previous slide. So this is a function of disjoint distribution. So this is the heat map of disjoint distribution is a function of mu and sigma. Okay, and this is the posterior. This is a heat map of this function here when plotted as for mu and sigma. And what we can see is that basically the prior prefers values that are centered here, right? The purple cross. The likelihood term prefers values, this is the data term, prefers values that are centered here. And if we multiply those two together, this is what's going on here, right? Then we get this plot. And that function, or that prefers values that are here. So they lie somewhere in between the prior, the mode of the prior, and the maximum likelihood estimate. Which again kind of makes sense because intuitively we want basically a trade-off between data and prior knowledge. Okay. Does this plot, these plots, do they make sense to everybody? This is kind of important. Okay, now algebraically, how do we go about maximizing this expression here? Well, we do this, basically, we apply the same trick that we have used before. So we take the log of all the individual terms. So this turns into the sum. This is the log of the Gaussian density for each data point. This is the log of the normal inverse gamma distribution that we've seen, I think, 2 slides back. And then we can compute we can maximize this expression with respect to mu and sigma by taking the derivative and setting it to 0. And it's slightly more messy than for the Gaussian, but it's easy to do. And what we get out is this, those two expressions. So this is our maximum likelihood estimate for the mean, given the normal inverse gamma prior and our data. And this is the maximum a posteriori estimate and for the mean, and this is the maximum a posteriori estimate for the variance. Now, if we look at those very sharply, especially at the mean, what can we see, or can somebody perhaps give me an interpretation? I mean, it's almost written on the slide. So what would be the maximum likelihood estimate? It would just be this first term here, right? It would be the sum over xi's divided by I, right? This is the maximum likelihood estimate. And then this is basically the prediction from the posterior. This is this delta parameter determines where the mu should be, right, according to the prior. So basically what we end up with here is a weighted sum between the data mean and the prediction from the prior. And what determines the weighting between those two components?
Variance?
Sorry?
The variance?
The variance of what?
That's the real data.
No. So the real data comes in through the I, right? So that comes in through the number of data points. If you have a lot of data points, what will the weighting of the data go up or down? Up. Yeah. So if you have a lot of data points, this is going to be close to the maximum likelihood estimate of the mean, which intuitively makes sense, right? But you are right. It depends on the variance. or something like the variance, which is this gamma parameter here, which controls the spread of the marginal distribution of mu in the prior. So if we go back a couple of slides, sorry, I'm going in the wrong direction here, and then we stop. Where is this is slide? So this here is varying gamma. Okay, large gamma, small gamma. I believe. No, the other way around. Large gamma, small gamma, large gamma. And as you can see, for a large gamma, it's going to be a lot tighter. So we have a stronger prediction as to where the mean should be in our prior. And if it's small, we are less prior is less certain about, or we put in less prior knowledge basically about where the mean should be. Okay, and this is exactly what we see in this weighted average.
Sorry,
Yeah.
I cannot see from here the
numbers.
I cannot see the values from here.
Which lines?
For the diagrams of the like peaks and density of it.
Okay. You mean the numbers here?
Yeah,
So here we have a 0.4 for gamma, and here we have a 4.0 for gamma.
It's alpha, beta, gamma, delta, and then it's lower values after one. It's lower or bigger values or something.
I'm not completely sure I understand the question. Perhaps we can talk about this. I mean, this is the last slide I was kind of going to show, and the Bayesian approach and the other examples will come next time. So if anybody has any more questions, perhaps shall we talk about this afterwards, perhaps? Or if people want to leave, I'm not sure, we should stop at 55, right? Okay, well, ask you a question.
Can you talk about the last slide? About where is the prior mean in that? One more, two more.
Yeah.
There. Where is the prior mean? Why is that the prior mean?
So delta minus mu is minimized if mu is equal to delta. Does this make sense? Kind of. So if you only worry about so this is the prior distribution, right? So let's worry only about the mu. Okay? So mu only appears here. So the mode, which happens to coincide with the mean in this case, so the peak basically, as a function of mu is obviously going to be when this is a negative exponent. So if we minimize that negative exponent, and it's minimized if this distance here is 0. Yeah? It's the same as for the Gaussian distribution, where if x is equal to mu, then we have 0 in the exponent, and that's the mean or the mode of the Gaussian.
And why were you showing the Gaussians?
Why I was showing these?
Yeah.
These are on the slides. I mean, these are not my slides. No, I guess this gives you an impression of sort of how this plot here, which is really just the density of mu and sigma, right, under the prior, how those how points in this space correspond to actual Gaussians, right?
So there is no nice relation between mu and those 4 parameters?
Well, mu, this is sort of the prior mean, okay? So the delta is basically the mode of this, the delta corresponds to the mode of this distribution. The distribution over mu and sigma squared, right? If you only worry about mu, then the distribution is largest everywhere when mu, so for all values of sigma, when mu is equal to delta. Right? I mean, this is what we just discussed. So if mu is equal to delta, this is 0, and you can't really get this term any smaller by changing mu. and this term is then going to be maximized as a function of mu. Does it make sense? Not really? Well, we can talk about it a bit more. The other thing is the gamma here controls basically how widely that is going to, how wide the spread of mu is here, right? This is what I was trying to show on this plot here. So as we change gamma, we'll get a larger values of mu basically become more likely under the prior. So this is a small gamma means a wide spread of the mu value, and a large gamma means a small spread of the mu value. The gamma is basically, you can think of it as an inverse of this sort of variance, but we can talk about this a bit more. Any other questions? No? Okay.